Here we are talking in this lesson, 3.3, about using combinations, which we talked about in our last lesson, but we're going to solve some problems with combinations. We're also going to talk about subsets, and that's what I'm going to begin with. A subset is a group of objects chosen from an entire group of objects, and it may include any number of elements from all to none, where order and selection is not important. So let's just show what we mean by that. If I want to list all the possible subsets from the set of a dog, a cat, and a fish, let's do it. So I'll add, D, C, F, so I don't have to write the words out over and over. Well, the first subset could involve the dog, the cat, and the fish. Maybe I want all of them, right? I'm choosing a pet, and I choose all three because I love animals. So that's a possible subset. And again, it's a subset, so order doesn't matter. It doesn't matter if I say fish, cat, dog, or fish, dog, cat, or cat, fish, dog. They are all the same. Order doesn't matter. So that's one subset. Maybe I am allowed to get two of them, right? Maybe my wife will only let me get two pets. Well, then I could get the dog and the cat, or the cat. I could get the dog and the fish. I could get the cat and the fish. But that's it, again, because order doesn't matter. Maybe I'm only allowed one pet. Dog, cat, or fish. That's my only options. Maybe I'm allowed no pets. So sad. We call that the null set. That zero with a line through it. We can call that the null set. There's nothing in it, but we can still consider it a way to come up with a subset. So how many subsets are there? Well, there's one, and there's three here, and there's three here. And if we count this one, then there's one. So it looks like there's 8 different subsets that I can come up with from those 3 elements. Therefore, to calculate the number of subsets of a group with n distinct elements, we use the formula n of a equals 2 to the n. So what they mean by that is however many elements are. In this case, in the example we just did, there were 3 elements. So I could have predicted that there was going to be 8 subsets in this case, because 2 to the 3 is equal to 8. So if we were to add, for example, a 4th option, and maybe I wanted to have a bird as well, then I'd have 2 to the 4 possible subsets. Turns out that there'd be 16 different possible subsets by adding a bird. If I added yet another animal, let's call it, say, an armadillo, then now we're up to 32 possible subsets, and on and on. So every new element we add actually doubles the number of possible subsets. Kawartha Dairy has 12 different flavors of ice cream. How many possible subsets could there be is you want some ice cream? I think this should say if. Call me crazy. All right, if you must have some ice cream. Well, what we're saying here by if you must have some ice cream is just another way of saying don't count the null set. We're not allowed to not have any ice cream. So in that case, we have to adjust the formula slightly. We're going to subtract 1. So if we don't count the null set, I'm going to write this up here. If we don't count the null set, the formula is n of a equals 2 to the n minus 1. So it's that minus 1, which is just the new addition to the formula. So if I want some ice cream, I could take all the ice cream. I could take one of each. Or I could take 11 of the 12. Maybe I just don't like buttered pecan. So then I'd have, but then there'd be 12 different ways I could choose 11 out of the 12. And so on, going down the line, but it'd be 2 to the 12, and then take away 1 because we're not going to count that null set. I got myself a new calculator since last time for combinations, which I don't need in this case, but it's good to know it's handy. So if I do 2 to the exponent 12 minus 1, my answer is over on the left hand of the screen. Sorry, my question's over on the left hand. My answer's over on the right. If you look over the right, it says 4,095. So there's 4,095 ways that I can have some ice cream out of the 12. If I'm feeling greedy, I can have all 12. If I'm feeling not so greedy, I could have just 1. I can't have none. Oops, I did not mean to go away from there. There we go. Here's a recollection of the combination formula. Remember, it's the same as the permutation formula, except we got that extra r factorial on the bottom, and it tells us the number of ways that we can count things up if order doesn't matter. So, the card game Euchre. You may have played this. It uses only 9s, 10s, jacks, queens, kings, and aces. Those are the only cards. So there's 4 9s, 4 10s, 4 jacks, 4 queens, 4 kings, and 4 aces. So the total, if there's 4 of each of those, is 24 cards that's used. That is our N for our combinations. Determine the number of ways of being dealt a 5-card hand of, and let's see, at least 3 jacks. So again, that old at least thing. Maybe I want to use the indirect method, but maybe I don't. The way I decide is I decide which is going to be more work. So if I'm being dealt 5 cards, if I want at least 3 jacks, I could have 3 jacks, or I could have 4 jacks, and that's it. You might think that you could have 5 jacks until you stop and think about it and remember that there's actually only 4 jacks in the deck. So if I want at least 3 jacks, my only options are to have 3 jacks or 4 jacks. That would be the direct method. Okay, that's the direct method. The other method, the indirect method, would be to find what I don't want and then subtract it from the total amount. Well, what I don't want is a hand with no jacks, or 1 jack, or 2 jacks. So in this case, indirect way, I would have to do 3 calculations compared to the 2 from the direct method, 0, 1, or 2, and I'd also have to subtract that from the total number of hands, so that's actually a 4th calculation. Definitely the direct method is less work in this case. So let's go with that. So 3 jacks, I'm going to set it up like this. 3 jacks, almost like a little table. So to get 3 jacks, there's 4 jacks to be had, and we want 3 of them. So 4 choose 3. As we saw with the Lotto 649 problem from the previous lesson, we still have to account for the ways, for the other cards or the other things that we don't want. So if we want 3 out of 4 jacks, then that means that we want 2 of the rest of the cards. Well, how many of the rest of the cards are there? Remember, we started with 24 cards. 4 of them are jacks. That means that 20 of them are non-jacks, and we want 2 of those non-jacks. We also could have 4 jacks. That's another thing that would get us what we want. In that case, we want all 4 of the jacks, 4 out of 4, and we just want 1 of the 20 other cards. Now, if we go back to some terminology we used in the first unit, getting 3 jacks and getting 4 jacks are mutually exclusive events. Either I can get 3 jacks or I can get 4 jacks. I can't get both at the same time. So what I have to do then is add together the 2 different possibilities. It's this or that. That's the rule of sum for mutually exclusive events. So I can put this in my calculator. So I'm dying to try my new Desmos scientific calculator. Okay, so function. And you can see for this one down the bottom left-ish, I've got NCR. For this one's set up like we saw in the last lesson, where I, let me just remind you that there's different ways of writing combinations. Back up at the top of this note, we saw that we had NCR equals C bracket N comma R equals bracket N over R bracket. The one that this calculator happens to use is a variation on this. It says NCR and then puts N and R in brackets. So that's the way I'm going to type it in, NCR. So inside the brackets, I want, what did I want? I wanted 4, choose 3, 4, comma, 3, in bracket. Then I want times another NCR, which I find under the function tab. And for that one, I wanted 20, choose 2, comma, 2, end bracket, plus NCR of 4, choose 4, times NCR of 20, choose 1. And again, it does my answer as I go along. It turns out that there's 780 ways to get 3 jacks or 4 jacks. At least 2 clubs. Well, again, let's decide. We got at least, so we have to decide what's going to be less work. At least 2 clubs means I could have 2 clubs. That would be something I want. Or 3 clubs, or 4 clubs, or 5 clubs, because there's actually 6 clubs in those 24 cards. A quarter of the cards are clubs, so the 6 clubs, I could have 5 clubs. So 2, 3, 4, or 5 clubs if I do it directly. Or I could do it indirectly by taking the total hands and subtracting having no clubs or 1 clubs. That one, in this case, it seems like the indirect method is actually going to be less work. So total hands minus 0 clubs, in other words, hands with 0 clubs in it, and hands with 1 club in it. All right, so we need to calculate these 3 things. So total hands, I'll set it up like a table again. That's going to be 24 cards, and I just need to choose 5 of them, no restrictions. 0 clubs, that's going to be, there's 6 clubs, so I want 6, choose 0. Anytime we choose 0, though, we know that just equals 1. So there's one way to choose none of them. So that really doesn't factor in it. Though I still write it down so it's accounted for, it's not going to affect my outcome. But then I have to choose, there's 18 non-clubs, and of those 18 non-clubs, I have to choose all 6. And then if I want 1 club, then I would have 6, choose 1 club, and I'd want 5 of the 18 non-clubs. So again, no, not subtract, not add, I mean. So I got the total hands, and then I want to subtract both clubs, and both 0 clubs and 1 club. Actually, it's probably better to write it like this. Not use the brackets. I just want to subtract both of them. So I got the total hands, subtract the number with 0 clubs, also subtract the number with 1 club. And again, I can do that all at once on my calculator. So what did we have? 24 No, not sign. Let's clear this. 24, choose 6. Minus 6, choose 0. Sorry, just hold on a second. My apologies, just had a brief interruption. All right, so we're going to subtract 6, choose 0 times 18, choose 6 minus 6, choose 1 times 18, choose 5. And I got 60. Oh, I did something wrong here. Sorry, I was looking at my answer thinking, that's not right. It wasn't 24, choose 6. It should have been 24, choose 5, shouldn't it? Because there's only 5 cards in the hand. That's not right. Okay, so what have I done? Okay, I see. There's 5 cards in the hand. So let me make a slight adjustment. I don't want to restart this video or anything, but sorry. So 24, choose 5. Yes, there's 6 clubs. All right, so where I went wrong was I was getting my 5 cards and my 6 clubs mixed up. So everything's good up to here. This one I need to change to a 5 because 6, choose 0 clubs. Okay. No, I do have to change a few things. I'm just going to get rid of this. I'm going to rethink it. So there's 24 cards. We're choosing 5. That's fine. So of the 6 clubs, I want to choose 0. Yes, that makes sense. And of the 18 cards that are left, I want to choose 5. That's something I changed. And then of the 6 cards I had here, I want to choose 1. And I think I already had that. And then of the 18, I needed 4. So I needed to change those 2 numbers there. So let's change that on my calculator as well. I think the only thing I need to change is this needs to change to a 5 here, and this needs to change to a 4 at the end. That's better. Apologies, but we all make mistakes, and it's always good to double check our work, so there is a lesson involved here. In this case, I happen to recognize that the number was not the number I was expecting. The number I was expecting was there's 15,576 ways to have at least 2 clubs in a euchre hand. Now, the number of ways to have no face, no ace, no trump, that is, if you ever played euchre, you may have heard of that one. So, basically you have to have just 9s or 10s, and so there's only 4 9s and 4 10s, so there's 8 cards. However, trump is, as it says, the designated ruling suit for the hand. So that's going to change from hand to hand, but let's, for argument's sake, that someone made hearts be trump. So hearts is trump in this particular hand. That means that instead of being the 8 cards, we're actually we have to take away the 9 of hearts and the 10 of hearts. So we have to take away those 2 cards, and there's only going to be 6 cards to choose from. So 6 cards. So of those 6 cards, we have to get 5 of the 6 cards. So it'd be 6, choose 5, which is just going to equal 6. We don't even need a calculator for this one. If we remember the formula, it's 6 factorial over 6 minus 5 factorial, which is 1 factorial times r factorial. And 1 factorial is simply equal to 1. 6 factorial divided by 5 factorial reduces to just 6. There's 6 ways to get no ace, no face, no trump. And then if you remember, there's 24 choose, 5 ways, total hands. That's an awful lot of hands. It's very unlikely that you're going to get no ace, no face, no trump. But it does happen. It's happened to me in the past. So I guess it just goes to show that just because something's unlikely doesn't mean that it's not possible. Anyway, there you go. Good luck with the homework questions, and I will talk to you in the next lesson.